Solution for the second packet of chemistry for the summer work. An atom has 65 neutrons, so N is equal to 65. You have a mass, which is the A number, which is 122 units. Write the proper nuclide symbol. So if you have 122 as a mass number, that means that your protons, right, this is equal to neutrons and protons. So this means that your number of protons are equal to 122 minus 65. Okay, so this one will give you 57. So your element is going to be La, right? And the mass number up here, you write 122, and the number of protons you write here as a 57. Number 2, an atom A has 11 neutrons, and the atom B has 11 neutrons as well. Are these atoms isotopes? Definitely not. And the reason is, to be isotopes, you have to have the same number of protons. So the atoms have to be representative of the same family. So for example, for the potassium, every element has to be potassium. So they all have to have 19 protons, but number of neutrons can be different. So the mass here for potassium is 39, and let's say, it's a little bit more than that, but it's 39. So if 19 are the protons, you can have a 20 as a number of neutrons, but you can also have a 21, you can have a 18 maybe. So all of those are isotopes of the element potassium, but you got to have the same element, which is called potassium. Which component of Dalton's atomic theory reflects his understanding of the law of conservation of mass for chemical processes, and why? Well, he says that in a chemical reactions, you can readjust elements, but you cannot create, you cannot destroy elements. Well, he doesn't necessarily speak about creating or destroying, but he speaks about the fact that you got to have a rearrangement of atoms. So that's already good enough to conservation of mass, for conservation of mass. Number 4, the atomic mass of elements are generally not whole numbers. Explain why. So the atomic mass is basically the number that you read in the periodic table. So as we said, you have isotopes of the same element, right? So when you average them up according to the weight, right, and the abundance of the presence of those particular isotopes, when you do the calculation, you have decimals, okay? So those are not whole numbers. So let's clear this up. Okay, so number 5. Number 5 says gallium has 2 stable isotopes. So you have this mass here, okay, and gallium-71, which is this mass here. Using the average atomic mass of gallium, what is the percentage abundance of the heavier of the 2 isotopes? So what you should do at this point is to take, for example, so 68.92 is present for X percent, right? You also have 70 plus 92, which is present for 100 minus X percent. And this is equal to your mass in the periodic table, which is 69.7. Okay, from here you solve, and you have that when you calculate your X, when you do 100 minus X, this is basically the abundance of the heavier one, which should be 39.9, 40%, whatever. Okay. Then number 6, naturally occurring chlorine is present for, so this is 75.78% this mass, and 24.22% of this mass. Calculate atomic average mass. So again, you write down the 75.78% of the mass, which is the 34.9689, and you also add the 24.22%, sorry, you can see it probably, of the mass, which is instead 36.9659. You do your calculation, and you should have a mass of 35.45 atomic unit. Okay? This is number 6. Number 7. What conclusions were made from Rutherford's gold foil experiment? How did the experiment change the atomic model? Well, Rutherford came after J.J. Thomson, who thought that the model looked like a plum pudding with protons and electrons smeared in this uniform ball. But because of the Rutherford experiment, when he was targeting the aluminum foil, he saw that not every single one of those alpha particles were going through the aluminum foil. Remember that the alpha particles are 2 protons, so 2 protons are high speed, should be able to perforate the aluminum foil, basically, okay, and to be detected on the screen behind the aluminum foil. Because this didn't happen every single time, but the majority of those particles were deflected, this conclusion made think of a bigger repulsion toward the high-speed 2 protons particles. So because of the repulsion, because of this force, the repulsion should be created, let's say, or made basically by a bunch of protons instead stationary in the nucleus, almost stationary. So this means that basically the protons are stuck, are packed in the nucleus in the center of the atom. Then number 8, explain why the Bohr model was insufficient and how the quantum model explained the deficiency, and how is the electron viewed differently in each model. So for Bohr, remember that we were supposed to have atoms all at the same, so you have the nucleus here, okay? And then you got to have specific orbits, okay? So those electrons are traveling, are revolving in these orbits of very specific energies, okay? And because those are specific energies, he has calculated in his mind, well, not in his mind, he has calculated the distance, okay, between those orbits. Now, the number of electron volts necessary to keep the electron in the orbital, okay, is a specific number that is just valid for the hydrogen atom. Any other atom, for any other atom, the electron volt number is different. So this means that this model is not necessarily true. His problem was, first of all, so 2 main mistakes. The first mistake was that there are no specific energies, but if this is the nucleus, you have situation, right, waves where those electrons can be. So you have cloud of possibility where the electron can be, right? A lot of clouds. So places where the electron definitely cannot be, like here, cannot be, but can be anywhere in this cloud, right? So has this kind of deficiency, and also has deficiency referring to the fact that he's talking about level of energy n equal 1, n equal 2. He's not considering that in different levels of energy, you might have different orbitals. You can have the orbital S, P, D, F. He does not take care of those at all. Nevertheless, his contribution is fundamental because it is the first step for the evolution, basically, of this model, which is the one of Heisenberg, which is this one. So this is the Heisenberg model. This is the Bohr one instead. Okay, and then number 9, consider the equation relating wavelength, frequency, and energy. So let me clear this. Of electromagnetic radiation. How is the energy of a photon related to the frequency and wavelength? Well, we know two equations. So we know that the energy is equal to h, which is the Planck number, times the frequency. And we also know that the wavelength is equal to speed of light over frequency. And obviously, because of this, we can reverse and we can do the frequency equal to the speed of light over wavelength. So at this point, is saying how is the energy related to the frequency. So this is how it's related to the frequency. But also we can say that this is h times, if for example we do not have the frequency but we have the wavelength instead. So we got to substitute this equation here and put the c over lambda, because c over lambda is frequency anyway. So the E is directly related to the H, right? So E and nu, the frequency, are directly related to H. And instead, E, this is times lambda, I want to say, is equal to Hc, let's say. So those are instead inversely related. Which one was this? Okay, 9. Number 10. So here. Number 10, calculate the frequency of an X-ray that has a wavelength of 8.21. So you have the wavelength, so you use this equation for frequency, right? Don't forget that C is equal to 3 times 10 to the 8, okay? So the frequency, you got to do the C divided by the lambda, and you should have a number which is 3.65 times 10 to the 16th hertz. Okay, number 11. What is the frequency of a photon that has an energy of? So we want the frequency, so we are using this equation here. Okay, so frequency from there is equal to E over H. So they are giving us the energy, which is 3.7 times 10 to the negative 18 joules. Divided by Planck's constant, which is 6.626 times 10 to the negative 34 joules seconds. And so we have a number that is 5.6 times 10 to the 15 hertz. Number 12, provide a brief explanation of what each of the 4 quantum numbers describes. So N is the energy level where the electron is. Then you have the, what is this? So then you have the number L, which is in particular the particular orbital, okay, in which the electron is. Then you have the M orbital. Okay, M orbital gives us the shape. Okay, not just the shape, tells us exactly in which part of the orbital the so let's put it like that. So tells us okay, M tells us in which portion of the orbital, okay, the electron is. So for example, L can say, so this one can say level 3, energy level 3. L will say at this point that we can have an orbital S, an orbital P, and an orbital D. So 3 of those, right? And then for M, we can say that S, right, is made of only one possibility, one shell, one situation, one room. And then P instead is made of 3, right? So this is the one that tells us that this is the dumbbell. And D instead is made of 10. So this one is instead the other structure there, okay? Okay, so those are the things. And then you have the spin, okay, the MS, basically. okay, and tells us the spin of the electron, which can be upward or can be downward. So basically it can be plus or minus 1/2. Then number, oh, that's it. Okay, so for the homework portion instead. So we have radioactive americium 241 is used in household smoke detectors and in bone mineral analysis. Give the number of electrons. So we have americium, which is Am, and so what does it say? And this is 241. So this is the mass. So 241 has to stay on top. Then okay. So this is the isotope 1, which is radioactive and actually emits alpha particles, but nevertheless. So protons, the proton number is 95, so 95 goes right there. So electrons, if it is neutral, obviously, so the protons are 95. The electrons are also 95. And the neutrons, in this case, for this particular isotope, is 241 minus 95. Okay, so that will give us 146 as number of neutrons. Then, okay, number 2. So I write the proper nucleide symbol, so that's the one. Okay, so number 2, what characteristics do atoms of carbon 12 and carbon 13 and 14 have in common, and in what ways they are different? So they are all carbons, so this means that every carbon contains 6 protons, but the number of neutrons in this case is 6, this is 7, this is 8. Identify the isotope that has atoms with 117 neutrons, 77 protons. So right there, let's go for the 77 protons. And you find that the first one is iridium. So the first one is iridium. And then this one has 28 protons. So go for 28. And you have nickel. So this is nickel. Then number 4, how did the discovery of isotopes conflict with Dalton's atomic theory? Oh, he didn't believe in the number of, he didn't believe in the existence of isotopes because one of the postulates said every element in the same family of every component of the family of the particular atom has to be exactly the same, and it's not true because every element can be part of the same family, but they contain different numbers of neutrons, so that is not true. Number 5, the average mass of any large number of atoms of a given element is always the same for a given element. Explain. If you have a big enough, if you have a very abundant isotope that has the mass that is close to the average mass, then you can say that this situation is true. Naturally occurring boron is 19.9 of mass 10.01, blah, blah, blah. And 80% instead, 0.1 is of the other mass. Calculate the average mass. Again, and you do the 19 over 100 times 10.01, blah, 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 plus 80.1% of the mass 11.00, blah, 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 and you find the average mass. And you should have a 10.811. Then, number 7, uranium has an atomic mass number equal to 238, blah, blah. It consists of 2 isotopes, uranium-235 with that mass and uranium-238 with the other mass. Calculate the abundance of the 235. And again, you proceed like we have done already, and it's 72%. 0.72% for the 235. In fact, you have a mass, average mass that is 238.0, right? And then you have uranium 238, which has a mass of 238.0. So the majority obviously is coming from the 238, which makes sense because 235 is the one necessary for the nuclear reactions. So the percentage of existing uranium 235 is so small that makes the quest pretty difficult anyway. And then this is 7. 8. How did Rutherford interpret the deflection of alpha particle in his gold foil experiment? Did this finding support or disprove the plum pudding? And we just said that it disproves blah, 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 and we just explained that before. How does Bohr's model of the atom explain the existence of line spectra? And how are spectral line produced? So when you have those electrons that are excited because of a source of heat, so those electrons are going to jump up to a higher level of energy. But then once they are far away from the source of heat, then those electrons come back down. When they come back down, they emit radiation that is visible, and this is the emission spectral lines that we can see. And the distance between every spectral line, or the number at which the spectrum line is found, gives us the distance between the different orbitals. And what is the energy of a photon that has wavelength? We know how to calculate those. So number 10, the answer should be 2.39 times 10 to the negative 10 joules. And number 11 instead should be 379 nanometers, or you will find 379 10 to the negative 9, or you can find 3.79 10 to the negative 7. Each of those are always the same. And then number 12, the quantum, how does the quantum model describe the location of an electron? So again, according to the quantum model, which is the one from Bohr, the electrons are situated on a particular orbital level of energy. So class work for this one. So, okay, an element is found to gain 3 electrons when it forms an ion. What group number would this element be found in? Has to be in the group 15, because can only be nitrogen, phosphorus, aluminum, bismuth, and antimony. So those elements there. So we know there is in that group, but we don't know the period. We can determine the period because that depends on the particular level of energy in which the valence electrons are located. Number 2, look at the average atomic mass for argon and krypton. Argon and potassium. So argon is 39.9, potassium is 39.1. Explain why early scientists might have been tempted to have K follow Cl, so chlorine, on the periodic table. Because in order you would put 39.9 before 39.1 before 39.9, according to the mass number. But instead, we are allowing stuff, we are locating stuff in the periodic table according to the increasing number of protons instead. Propose 2 reasons as to why they placed argon after chlorine instead. Well, I just said it, because of the presence, because of the number of protons, right? Because it's 17 for chlorine, 18 for argon, and 19 for potassium. The other one could be the electronegativity. Because chlorine wants to gain 1 extra electrons, whereas argon doesn't, and potassium wants to give it out. So it would not make sense for potassium to be in the same column as a noble gas, for example. So number 3, identify the following element. Alkali metal in the 5th period. So fifth period is rubidium. Transition metal in the five element, in the five level of energy, the fifth level of energy, could be the fifth, a transition metal. I don't know in which period, not sure which one they are saying. Okay, so it could be any transition metal, I guess. And then an atom that is in the third period instead. So third period, and forms a stable ion with charge -1, and that would be chlorine. Explain why atoms tend to gain or lose electrons relative to the number of valence electrons. So atoms gain or lose electrons to obtain the full valence electron, so that they can become noble. And which ion are the following element likely to form? Nitrogen. So nitrogen will form a 3-, calcium will form a 2+, and sulfur will form a 2-. Explain why the noble gases are inert. Well, because they have no orbital available for any electrons to be welcomed in. Why are the charges of transition metals, D block, difficult to predict? And that would be because they can lose 2 electrons from the outermost S, but also they have element in the, some electrons in the D electrons that can be lost as well. So it really depends how much energy is the least amount that is going to be absorbed in order for the electrons to be able to jump up and connect with something else. Write the formulas of the following binary ionic compound. So for those, the color is here. Okay. So magnesium oxide. Magnesium has a charge of +2. Oxygen has a charge of -2, so you put them together and becomes magnesium oxide. Manganese with a charge of 2+, and chloride, which is a charge of -1, and becomes an NCl2. Then you have calcium phosphide. So calcium comes with a charge of 2+, and phosphorus, so the phosphide is -3, so that's a negative. So you have calcium 3 and phosphorus 2. And then copper 1 sulfide. So copper has a charge of 1, sulfur has a charge of -2. So when you put it together, you have a copper and 2 sulfurs. Write the formula for the following polyatomic ion compound. So potassium phosphate, sulfate. So sulfate has a SO4 with a charge of -2. So you need a 2 here. Sorry. And then aluminum phosphate. Aluminum has a charge of 3+. Phosphate has a charge of SOPO4 -3, so this is staying as it is. And then iron 3 carbonate, so iron with a 3 carbonate, this one has a charge of 2, so you need 3 of this and 2 of that, so that we have a 6 and 6. And then aluminum with a charge of +3, hydroxide, which is this, forms AlOH with a 3 there. Okay. Next, aluminum. Okay, aluminum reacts with a certain non-metallic element to form a compound with a general formula. So let's write it here: Al2x3. So now aluminum, just in case, let's remember that this one is a +3 and this one has to be a -2, right? For the crisscrossing situation. Element X must be formed from which element in the periodic table? Well, it has to be in the oxygen column, okay? So in the column 16. And that's done. So homework. Now those are exactly based off the same concepts. So what accounts for similarities? What accounts for similarities of chemical properties for elements in the same group family? So they have to be able to have the same number of valence, basically. Provide the group name for the element for the group 1. So group 1 is alkali metal, group 2 is alkali earth, 17 are the halogens, and 18 are the noble gases. And provide an example. Okay, so for group 1, lithium, for group 2, beryllium, for group 17, fluorine, and for group 18, neon. Identify the following element, halogen in the third period. So that one has to be chlorine. A metalloid can be boron, can be silicon, can be germanium, can be any of those. An element in the fourth period that forms a stable ion with a charge of +1. And that would be potassium. Locate the following element. I think you can do that. Okay. And then mole concept and homework. Okay. So mole concept. Okay. So answer the following question. What is the molar mass of the aluminum sulfate? So first of all, you got to write the aluminum sulfate. So that's a 2, that's a 3. Then you do the mass. So this is 27, I want to say, yeah, 27 times 2, so this is 54, plus 3 times 31, no, 32.1, I think. Let's check, yeah. And then plus 12 times 16, you add them up and you have your mass. So, and this is 342.15. 342.15 grams per mole. What is the mass of 1.5 mole sample? So this is 1 mole. So 1.5, you got to multiply this one by 1.5. Okay, so 1.5 times 342.15. So 513 grams. Cannot say per mole because this is 1.5 moles. Then, how many oxygen atoms are present in, what is it? In 1.5 mole sample. So, in 1.5, so let's write it here. In 1 mole, okay, so first of all, 1 mole contains, okay, how many molecules? Contains the, we have 1.5 moles. 1.5 moles. And then this is 1 mole contains 6.022 times 10 to the 23rd molecules. Okay, and then we got to keep on going because 1 molecule, okay, they are asking for oxygen, so contains 12 atoms. Okay, and should be 1.08 times 10 to the 25th atoms. Okay, 36 grams of gallium, okay, is such that has a, so gallium is 69.7 grams in 1 mole, 52, 0.52 moles. So first of all, you got to divide this one by, so 1 mole contains the Avogadro number times 10 to the 23rd atoms, because it's just a gallium. Okay, so this is 6.022 10 to the 23rd times 0.52. So this is basically 3 0.13 times 10 to the 23rd atoms, okay, of gallium. Now, what is the mass of rhodium? So the atoms, again, 6.022 times 10 to the 23rd atoms are in 1 mole of rhodium, and rhodium is right here and is 102.9. So 1 mole is 102.9 grams. Okay, so this is 1/2, so almost, right? So this is 3 10 to the 23rd. This is 6 10 to the 23rd. So basically this is 1/2, so 102 divided by 2. So it's about 51. Okay, if you do all the calculation instead, so this is 53 actually. 53 grams. Okay, and then the same thing for 36 for the indium instead. So how many grams of how many moles of indium we have? Okay, so you can also shorten this process up a little bit. First of all, how many moles are there? So you can do 36 grams of indium, right? So we want to know how many atoms are in there. So we know that in 1 mole of indium, there is a weight of 114.8 grams, okay? And then, so this is the moles, and then in 1 mole, we know that there are 6.022 times 10 to the 23rd atoms, okay? Now, this number has to be equal to, so whatever this number is, okay? So we are going to have, let's say, indium atoms, okay? So now we want to know what is the mass of the rhodium that contains that many atoms. So we start from the atoms, whatever this number is. So technically, we can keep on going from here, okay? So whatever this number gives us is the number of atoms. So let's say that this is 25 atoms. Obviously, it's a lot more than that, okay? So we got to go for atoms, okay, and in 1 mole. So we know that there are 6.022 times 10 to the 23rd atoms in 1 mole of rhodium, right? Rhodium. And then, so we want to know the mass, and then 1 mole of rhodium has a weight of, what did we say before? It was 102.9. Okay, so as you notice, basically this fractions, we can just skip it all together. Okay, this is 1 and 1. So basically we have a 36 times 102.9 divided by the 114.8. In the other situation, instead was 36, it was gallium, right? Times 102.9 divided by the mass of the gallium, which was 69.7, right? So basically, the only thing that changes is this number here. So 36 times 102.9 divided by 69.7. So like we said, we have a 53.1. And then for the other one, instead, is 36 times 102.9 divided 114.8, and we have a 32.3. Okay, and those are the answers for that thing. Then calculate the mass in grams of this many moles of calcium nitrate. Well, calcium nitrate is NO3, and you need 2 of those. Okay, so what is the mass in grams of the whole mole? Well, you got to do the whole 40.1 plus 2 times 14, which is 28, plus 6 times 16. Okay, you add them up. So 40.1 plus 28 plus 6 times 16, and you have 164.1. Okay, so those are the grams per moles. But then they are asking for 0.433 moles. Okay, so what is the grams now? So this one times 0.433, and you have a 71 grams, 71.1. Okay, how many formula units of calcium nitrate are present? So formula units, remember, we cannot talk about molecules because this is ionic compound, right? But nevertheless, so in our mind, we can say how many molecules, okay? And that would respond to the answer for formula units. So you have 71.1 grams of calcium nitrate, okay? So how many molecules are there? So we gotta go to moles first. So 1 mole is made of 164.1 grams, okay? And in 1 mole, there are 6.022 times 10 to the 23rd formula units, okay? So 71.1 divided by 164.1 times 6.022 E23, and we have a 2.61 times 10 to the 23rd formula unit. How many nitrate ions are present? Well, the nitrate, okay, is 2 per molecule, so it's twice as much, right? So 5.21. And then carbon has 2 isotopes. How many atoms of carbon would be present in 34 grams sample of pure diamond, which is the same as pure carbon? So 34 grams. And then 12 grams is the pure carbon. And this is 1 mole. And then in 1 mole, there is the number of Avogadro. Okay, this one gives us how many ions of NO2 we have. Oh, what do they want? Oh, atoms of carbon. So 34 divided by 12, and then times 6.022 E23. So it's 1.71 E24. And then how many atoms of those are C13? Well, 1% of that, right? So this is the, so the 1.71 E24 is going to be the number of atoms for pure carbon. And then 1%, okay, so 1.71 E22 is going to be the percentage of atoms with mass 13 instead. Number 5. A sample of nickel hypocarbonite, a toxic transition metal complex, has this many carbon atoms. How many atoms of nickel does it contain? But the ratio is 4:1, so this number divided by 4. And then number 6, how many grams of CO2 are contained in 7.50 liters of CO2? So you have, you know that, okay, so let's start with this 7.50 liters, okay? And you know the 22.4 liters are 1 mole, of gas, right? So how many grams are there? You know that 1 mole also has a weight of, so this is 32, right? 32 plus 12. So this is 44 grams. Okay, so 750. Oh no, 7.50. 7.5 divided by 22.4 times 44. So it's 14.7 grams. Then number 7, without doing any detailed calculation, rank the following simples in order of increasing number of atoms. So that's the one you actually asked in class. Okay, so for this number here, for this one you have half a mole, okay, of H2O. So how many atoms are there? So this is the mole, right? And in 1 mole, there are the Avogadro number of molecules, and in each molecule, there are 3 atoms. Okay, so this means that this is 3 times 0.5, but we shouldn't do any calculations anyway, but just to understand, right? So this is 1.5 times the Avogadro number. This one instead is 23 grams divided by 23 grams per mole, so this is just 1 mole. So this is for H2O. For the sodium, this is 1 mole, and in each mole, there is the Avogadro number of molecules, and in each molecule there's 1 atom, so really there is not much going on there. So you have 1 Avogadro number. And then for the N2 instead, this is the Avogadro number of molecules, so this is already 1 mole. But if you have that many molecules, you have twice as much atoms. So you have twice the Avogadro number of atoms. So in order of decreasing numbers, you have sodium first, then H2O, and then N2. Then a reaction produces this much ammonia. How many grams of N2 must have reacted to produce ammonia? I think this one we did it in class. So what you do is you're producing the ammonia, NH3. To produce it, you need nitrogen and you need hydrogen. You got to balance your reaction, so you have a 3 here, you got a 2 there, and now it's balanced. And they are saying you're producing 0.0891 grams. You gotta go to moles, so divide by 17 grams per moles to have the number of mole. And then how many grams of this have you produced? Well, moles to moles, right? First of all, so you got to divide by 2 this number, so you got to divide by 2, and you have here the number of moles. And then at this point, you multiply by 28, and you have the number of grams for nitrogen. Assuming nitrogen gas was the entire source of nitrogen, all of it is converted to ammonia. How many liters? So now you know how many moles you have. Take the moles and convert it to liters. Remember that every mole is contained in 22.4 liters. So multiply by your number of moles, and you have how many liters are occupied. And then see how many liters of ammonia were produced. Well, from here you have the number of moles calculated, and do the same ratio, right? The many moles multiplied by 22.4, and you have the number of liters. Calculate the following quantities for a molarity of this. Calculate the following quantities for 0.2 liters of this. Okay, so you have calcium iodide. Okay, and for calcium iodide, you have 0.4 molarity. So this means moles per liter. Okay, and you have 0.2 liters. Okay, so how many moles are there? So 0.08 moles, right? Then how many grams of calcium iodide are required to prepare the solution. So for this one, how many grams? So once we have the number of moles, we can convert this one right into, so okay, 1 mole is made of, calculate the molar weight of this, right? So calcium, which is the 40.1, plus twice the iodine, which is 126.9. Add them up. So 126.9 times 2 plus 40.1, and is 293.9. 293.9 grams times 0.08. So there are 23.5 grams. Okay, so here 23.5 grams of this. So this one we said was 0.08. And then how many moles of I only we have? Well, you go from calcium iodide, okay, you break it down in water because this is molarity, so this means there's soluble stuff, right? So calcium is a 2 plus, and you also have 2 I minus, okay? So for this one you have 0.08, so here you got to have 0.16 moles, okay? And then 10, what is the concentration of a solution of sodium chloride obtained by dissolving 9.3 grams of sodium chloride. So sodium chloride is 1 mole. Sodium is 23 plus 35. So this is 58. So you have 29.3 divided 58. So you have 0.16 equal to 0.16 moles. So we want the concentration. That's why I know that we need moles and we need liters. So insufficient water to give this many liters. So the molarity is 0.16 moles divided by 0.35 liters, and is 0.46 molarity, moles per liter. And okay, how many moles of sodium ion are present in sodium phosphate? So you got sodium and you have the phosphate, so you need a 3 there. So this is PO4. We know that this is a charge of -3. So this is your solution. And how many moles of sodium ions we want? So we got to break this one up, and we have 3 times, right? The moles and a phosphate, which is 3 minus. So sodium phosphate solution has this concentration in this many liters. So if we multiply 0.75 moles per liter times the liter, 0.75 times 0.15, we have a 0.113. 0.113 moles. This means that for this one we have 3 point, what am I saying? So we have 0.3375. Okay, those are the moles. And what is the molarity of sodium ions? So now you got to take those many moles, right? You divide in the liters, which are 0.15, and you have a 2.25 molar solution. Okay, now the rest, guys, I believe is still the same stuff. So if you have questions, you can ask in class, but I think you should have it all, okay? And let me know, because that's what is left. See you tomorrow.